We're seeking a counterexample for this statement. If f of x is an integer for every integer x, then the derivative is also an integer for every integer x. So the first thing I want to check is if this is true or not, because if it's not, then there's no way I could have a counterexample. To have a counterexample, I need the first thing to be true and the second thing to be not true. So f of 0 here is actually a quarter, which means the original statement was not correct. The original condition, rather, sorry, not the statement. Yeah, f of x is not an integer for every integer x, so this can't be a counterexample. F of 0 for the second one is 0, but f of 1 is 3/2. So then f of x is not an integer for every integer x there. This cannot be a counterexample. If I take a look at C, then f of 0 is 0, and it is for D as well. F of 1 is then 4/2, it's 2. And f of 1 here is 1. So I haven't ruled them out. We need to look into more detail here. Now, you can actually prove that C and D are both integers for every integer x quite quickly. Let's consider if x was even, then we just have an even plus an even plus an even. Right, that will give me an even at the top. If I divide by 2, I'm still going to have a whole number. Well, if x is odd, then these two would give me an even number. An odd plus an odd is an even. And so with these two. So again, I'm definitely going to get an even number at the top. So this is always an integer. For D, what we could do is we could factorize out an x squared and write it as x squared plus 2x plus 1 over 4. And then write it as x times x plus 1 over 2 all squared. Now, if x is even, this will be divisible by 2, so it will be an integer. If x is odd, then x plus 1 would be even, and this would be divisible by 2. So I know that C and D are going to satisfy this first condition. So now we've just got to investigate the derivative. But let's look at both cases. Okay, f dash x for this one is going to become 4x cubed plus 3x squared plus 2x plus 1 over 2. And if I now put in x equals 0, I'm going to get a half again. So, in fact, that one is my counterexample. I can stop there. I only need to find one situation where it doesn't work. Let's, for fun, just prove that the derivative of d is always an integer. So differentiating gives 4x cubed plus 6x squared plus 2x over 4. That will then become 2x cubed plus 3x squared plus x over, sorry, not, yeah, plus x over 2. I could rewrite that as, I could separate the fractions. So it's 2x cubed over 2, which just becomes x cubed, plus 3x squared plus x. I could factorize out the x to give me 3x plus 1 over 2. So this part is always an integer. And then if I look at the right-hand term, if x is even, then I've got myself an integer because it'll be divisible by 2. If x is odd, then this here will be even. So that it will again be divisible by 2. So yeah, nice function, that one, D. This here, sorry, I don't want to put a box around it because that's not the solution. But yeah, D is an integer for every value of x, and so is its derivative. Nice one.